Hello everyone, this is paper 73 presentation presented by Elbaraa Refaie. Over the last decade, the use of machine vision and artificial intelligence has been widely spread out. The market size is expected to keep growing in the future. The demand on using machine vision and artificial intelligence has spread out dramatically to cover almost all the life aspects. We now can see AI application in agriculture, part inspection, and medicine, etc. Highway and road management is one of the fields that applies machine vision and artificial intelligence to facilitate the work to get better and accurate results for traffic control and analysis. For the machine vision, we have three levels of vision. The low-level vision, which deals with the pixels directly, it involves extracting the fundamental image primitives like edges, corners, performing filtering. So basically, the low-level image processing is not considered a vision, but it's the pre-processing steps before making sense of the visual world. Simply, we can say it's refining process. The mid-level tasks include more about understanding but not fully understanding, like motion understanding but not fully detect the motion. High-level vision works for image understanding besides video understanding. Now the question, what is the difference between the classification and detection? Image classification involves predicting the class of one object in an image, while the object localization refers to identifying the location of one or more objects in an image and drawing the bounding box around the object. On the other hand, the object detection combines these two tasks, localization and classification, to detect one or more objects in one image. We are going to discuss the different detection methods for different vision levels. First, difference method. It's only detected the moving objects by finding the difference between two consecutive frames. Therefore, it's used for background extraction. For example, in car detection, the cars will be detected as its moving object, while the road and the surrounding areas will be extracted as they are considered a background. Second method is the thresholding method. Thresholding is a type of segmentation where we change the pixels of an image to make the image easier to analyze. In thresholding, we convert an image from color or grayscale into binary image 0 or 1 based on the thresholding value that we choose between 0 and 255. We use the thresholding as a way to select the areas of interest of an image. Last, contour method attempts to extract curves that represent the object shapes from the image. Edges are detected based on the discontinuities in photometrical, geometrical, and physical characteristics of object in image. Moving to the higher level vision, convolutional neural networks. The CNN is designed in a way to imitate the work of the frontal lobe of the human brain that is responsible about the processing of visual information. Convolutional neural networks apply a filter to an input to create a feature map that summarizes the presence of detected features in the input. Filters can be handcrafted such as line detector, but the innovation of the convolutional neural networks is to learn the filters during training in the context of a specific prediction problem. But to understand more about CNN detection process, the neural network consists of an input layer, hidden layers, and output layer. The layers close to the input layer helps in classifying simple features such as edges, corners, endpoints, etc. On the other hand, layers on the deeper level gather the simple features to form more complex features. At the end, the top level combines all the complex features and make a prediction. Looking to the car detection process in the image, car and truck has a common complex features like tires, glass, and body. Based on how far these complex features matches with the object, the detection will be occurred. Moving to the next algorithm, region-based convolutional neural networks. It's upgrade of CNN, as CNN takes long time to detect the object. For RCNN, it may have been one of the first large and successful application of convolutional neural networks to the problem of object localization, detection, and segmentation. It uses an object proposal algorithm called selective search, which reduces the number of bounding boxes that are fed to the classifier to close to 2000 region proposals. Selective search uses local cues like texture, intensity, and color, etc. to generate all the possible locations of the object. After the region of interests are determined, it will be resized to be suitable to be fed to the CNN neural networks. But there is some limitation of using RCNN. It still takes a huge amount of time to train the network, as you would have to classify 2000 regional proposals per image. Second, it cannot be implemented for the real time. It takes about 47 seconds for 47 to 50 seconds for each image to detect. The selective search algorithm is fixed algorithm, therefore no learning is happening at this stage. This could lead to generation of bad candidate regional proposal. Next, we're going to fast RCNN to upgrade the speed. Instead of feeding the regional proposal to the CNN, which are around 2000 regional proposals, we feed the input image to the CNN to generate the convolutional feature map. From the feature map, we identify the region of a proposal and warp them into squares by using the region of interest pooling layer that using pyramids to scale the image. We reshape them into a fixed size so it can be fed into the fully connected layer. From the region of interest feature, we use a softmax layer to predict the class of the proposed region and also the offset values of the bounding box. Fast RCNN added a bounding box regression to the neural network training itself. Therefore, now the neural network has two heads, classification head and bounding box regression head. This multitask objective is a salient feature of fast RCNN, as it no longer requires training of the network independently for classification and localization. These two changes reduces the overall training time and increases the accuracy in comparison to SPP, special pooling pyramid net, because of the end-to-end learning of CNN. But it still have drawbacks of time, because it uses selective search to find out the regional proposal. Selective search is slow and time consuming process. Coming to faster RCNN, similar to fast RCNN, the image is provided as an input to the convolution network, which provides a convolution feature map. Instead of using selective search that consumes a long time, instead of using selective search on the feature map to identify the regional proposals, a separate network is used to predict the regional proposals. The predicted regional proposals are then reshaped using the ROI pooling layer, which is then used to classify the image within the proposed region and predict the offset values for the bounding box. In this table, you can see the comparison between the different features and for the features and limitations and prediction time. The faster RCNN is the best in terms of time, consuming 0.2 second per image, which maybe can use for real time. But fast RCNN and CNN and RCNN, it's use long time that cannot be used for real time detection. Last but not least, YOLO, you only look once. YOLO is an object detection algorithm that much different from the region-based algorithm mentioned previously. YOLO is a regression-based object detector. In YOLO, a single convolution network predicts the bounding box and the class probabilities for these boxes. YOLO, in order of magnitude, faster than other object detection algorithms. Their speed reaches to 45 frames per second, which make it a very good solution for the real-time detection. Another key difference is that YOLO sees the complete image at once, as opposed to looking at only the generated region proposed in the previous methods. But how YOLO algorithm is working? YOLO is taking an image and split it in S by S grid. With each of the grid we have take n bounding box. For each of the bounding box, the network outputs a class probability and offset values for the bounding box. The bounding box is having the class probability above the threshold that we predetermined value is selected and used to locate the object within the image. But YOLO still have some limitation. The limitation of YOLO algorithm is that it struggles with small objects within the image. For example, it might have difficulties in detecting a flock of birds, and this is due to the special constraints of the algorithm. Says the experimental results for the YOLO detection and counting for car counting system. As we can see, it can detect the class and the percentage of accuracy, and we use the line to detect to count the cars and the motorcycles based on YOLO version 3. As you can see, for the far objects or the small object at the end of the frame, the YOLO have difficulties in detecting these far cars on the right or at the end of the frame because the objects are small. For the counting algorithm, we use a point recorder. We use the line and the point recorder to record the line, and we record the area that the car passes through, so we guarantee that the car will not be repeat counting again. In conclusion, it's noticed during this research that YOLO has the fastest speed reaches to around 45 frames per second, which make YOLO as the best solution if you want to go for real-time detection. For car counting, we need real-time, that's why we use YOLO. Faster RCNN has the highest accuracy over all the algorithms. Single SSD single shot detector has the accuracy which nears to faster RCN, but in terms of speed, the SSD is a bit faster than faster RCNN. Based on the application, we choose our algorithm. If you want to go for application that needs a high accuracy, you go for faster RCNN. But if you want to have application, if you have application that needs a real-time detection, then the best choice is YOLO. Based on also how many frames per second and the camera and so on, you choose your algorithm. This is my reference list that I refer to this presentation on my paper. Thank you for attention.